And then, I guess, we're actually ready to basically discuss everything that we did, that I showed in the very beginning. And we should be able now to understand how the density matrix basically evolves as a function of time. So, basically what's going on here is that you start out with this term, 1/2 identity plus IZ, which is your thermal polarization, everything's in state alpha, right? And then you put Hamiltonian on the left and the right, and the Hamiltonian that we're looking at here is expressed as this term, omega 1 times t times Iy. And so what this represents is a pulse along y. So I guess for now, I'm not going to be talking about like rotating frame or anything like that. So basically, the way you can understand the pulse in a simple way is basically that you're just switching your magnetic field from being in the z direction from now, and then from a sudden it's just in the y. Right. And then all you need to do is solve the sandwich equation that applies for the static limitations, right? So you take IZ and you apply basically the sandwich relationship. So you have IZ with the cosinus, right? Because it starts at 1 and then is, and what grows in is x if you apply a y pulse. Right? And so if you choose it to be a 90-degree pulse, really what you do is you choose this term to be 90 degrees so that the cosinus goes to 0 and sinus goes to 1, so that after your pulse, all you have left is x. Right? And then basically after the pulse, you have ix. And now your Hamiltonian changes. Now that Hamiltonian, after you applied your pulse, is just the magnetic field along z, so it's omega naught Iz. And now we can look at how this evolves under this Hamiltonian, the term that you've created, Ix. And again, you apply the same sort of sandwich relationship, which gives you, again, cosinus with Ix, which is this part, and what grows in is Iy with the sinus. And then you can basically write out this in a matrix form if you like. And this is what you get. And then in an NMR experiment, this is kind of important to maybe remember, is that you usually choose to measure the I minus term. So this coherence right there in the spin 1 time case. And you solve the trace. So basically, the trace of I minus would grow. So actually, do you know what I minus looks like? I had it on the slides before, but just making sure that you remember. So, right. So I minus basically selects this coherence. Right. Yeah, right. And this is what you do. So you select this coherence. And then you measure this, you get the trace, you get this function, and then according to the magic of the Fourier transform, you get your spectrum. And I guess we should maybe just stop right here, and I don't know, because the time's up and stuff, and continue tomorrow morning if you guys are interested.
So, yeah. One other thing I would propose is try to clarify a little bit this thing that you're kind of hiding under the carpet, which is how we're certainly turning with a huge magnetic field along Z to nothing along Z and a small thing along X.
Yeah, I mean, like introducing rotating frame and stuff like that.
Yeah.
Sure,
I think this is important.
It is important, definitely. No questions asked. I just left it out just because.
Yeah, right. But we can do that. We can do that tomorrow. Sure.
Sure. So then, yeah.
I just want to
the rotating frame is what?
A
myth. Yeah.
The way I think of the coefficient
it's mathematical art.
probability of
that's all I can tell.
cuts that state, like something existing in that state. So you have a certain probability of something within like population state and also the coherent state. Shouldn't all of those sum to 1? Why is it only that the ones on the diagonal sum to 1?
I think it can be dimensional, but I don't think it's trivial.
I think the coherences are sort of they're not states per se, like they're.
But I mean, if you want to ask the question, we can do that tomorrow.
That are in the population. So what's going to happen is after the trace, when you do the trace with
if you want to, you can go for it now.
Take all the stuff that is a coherence, turn it into a population, and then that sums to 1. Well, it doesn't sum to 1 because the matrix is it's not like a unitary matrix. But
I don't know if this is a good way of looking at it, but usually on the coherences, we always have some evolution, and in some sense averages to 0, and the populations don't evolve under a certain Hamiltonian if they're so I'm not sure if that.
So coming in here, I didn't follow your
I'm not sure if this is a good thing to say.
Why is it only the trace that has to sum to 1 rather than basically why only the populations and the coherences, the amount of population density, or I mean, the amount of density in those doesn't affect
It's just how you define your basis. You define your basis as being along the z direction. You could just as well, even if you have spins, say, evolving in the xy plane, you could define your basis to be along, say, x, and then then if you wrote your density matrix in that basis, you actually have evolution between populations. They go like sines and cosines or something.
Right, but what I was asking was, the way I think of your coefficients is that there's like probability that a certain state exists. So if your coherences also have some sort of probability, I was thinking that, well, if you sum all your probabilities, you'd get 1. And why is it only that when you sum your
But coherences they're not states, right? Because they're the cross elements of the matrix. So
It actually corresponds to an ensemble of spins that are in non-eigenstates on average.
So again.
Okay, so then that would just that would then average to 0, like.
Yeah, so again, you've defined your basis of the populations only tell you probabilities if you measure along z. So spins are evolving; they're not doing anything along the z direction. So your probabilities don't change at all if the spins are doing something like in a z field.
Okay, so your coherences are different.
The coherences sort of describe what's happening along the transverse plane, I guess you could say.
Okay.
So in other words, Claudia, there is an experiment which I think is very interesting to illustrate the difference between a coherence and a bunch of states that are all around the place in a non-coherent fashion is the inversion recovery experiments. When you invert your spin, so you place the magnetization from plus z to minus z, and they all go back to equilibrium. And each individual spin will go through the transverse plane while doing that, right? It makes sense. But since they're all along z and the symmetry of this situation is cylindrical, they will go through the transverse plane in a totally non-coherent way, right? Whereas if they're along z and you tilt them by 90 degrees, you put them out. So it's not going to be all of them, but like in average, they're going to like the population that you had before is going to be retrieved in the coherence in the transverse plane. So you will have your spins in average mostly in the transverse plane along a certain direction. Whereas in their inversion, their recovery, they go through the transverse plane but in a total random manner. And there is no coherence.
Okay.
Was it right what I said here?
I think everything you said is 100% right. I'm not
I'm
quite
not
sure
how
how
that describes the
question.
problem.
No, this is the way I see it. But
Right.
I think it's right. This is the way I see it, and I think this is the.
Can you maybe express your thoughts on how it addresses her original question as to like how does that answer why the coherences don't have to like
So
do something?
maybe I can tell you how I see the density matrix real quick, which is basically.